Welcome everyone to my dissertation talk. We'll get to explore together how we can move our designs towards a mutual understanding between mortals and machines in motion for the sake of safety. Oh, okay. So to lay a baseline from, I think, a commonly held tenet, our systems need safety. As our society continues to mechanize, and not only mechanize, but digitally transform, we are entrusting more and more, not only our livelihoods, but our lives themselves to our machines. It's imperative that we avoid outcomes as simple as the nose of a plane tipping up too far, or the temperature inside of a reactor getting just a little bit too high. These critical quantities are things that we track dynamically as dynamic states and form the foundation of control theory. And with advances in safe control, like the work that we do here in Core's third floor, we're able to robustly prove that our systems can remain safe despite perturbations or misspecification within a certain family. Just to give one concrete example that will turn up often in this talk, we can analyze which states can reach a certain dangerous keep-out state. In fact, we are checking to see which states are upstream of that danger. We literally use the same partial differential equations for fluid flow and get viscosity solutions just the same to analyze which states are at risk of careening into disaster. Put this in mathematical language, x dot equals f of xu, where x is going to be drawn from Rn. Let me illustrate with a running example of a Dubin's vehicle, which will be moving in 3 dimensions, z, y, theta. Here I've drawn a slice of the zy plane. You can see the cars moving around and their current angle that they're heading. These moving sets are, in fact, the 2D slices of their 3-dimensional reachable set in terms sliced on the theta level of their current heading. So you'll see that they track exactly the direction that the car is heading. What these teardrop shapes actually mean will become clear when we consider that every choice of possible control sequence for a car that's going to be how far you turn the steering wheel will generate a unique trajectory. We'll assume that the vehicle is drawn, the steering angles are drawn from a bounded set that is a subset of the full control space, R of n sub u. And so this car example can only turn so hard to the left and can only turn so hard to the right. In this instance, maxing out at 1 radian per second. In between these two extremes, there are a continuum of possible trajectories. But we can start to gain some geometric intuition by seeing that from this starting state, the car has several options in order to avoid keep-out set. And so we call this state safe because there exists a control sequence U that is able to avoid K for all time. Inching the car forwards to the edge of this teardrop, we are able to see that at the edge of the teardrop, those hardcore steering angles only barely avoid. Same for this upper right, or this upper position, only the hardest left avoids. And here at the bottom, only the hardest right avoids. And so you get the theme that here on the border, there's only one possible safe recourse. In contrast, in the interior of the backwards reachable set, on the interior of this teardrop, no safe recourses exist. This car is doomed to enter the undesirable states in K. In contrast, the interior of the white region has a veritable infinitely continuous, or an infinite continuum of possible control choices that are acceptable. So it can basically do whatever it wants for this first time period. But the core of each of these safety certifications that we can provide are always built on certain assumptions. For the reachability example that I just provided, it's built on the assumption of the car's dynamics being governed by these differential equations. When reality does not match these equations, our certifications are worthless. Crossing this modeling gap is part of the art of safety certification. We can make robust control that's robust to misspecifications on the dynamics. And we can use some adversarial game theory in order to be robust to possible signals that might come in and disturb our steering wheels. But as industrious as we may be, there will always be a modeling gap. Even if we were perfect safety engineers and had a divine model that incorporated all of the features of reality, the map that we use to map from reality to our formalism will often break down just from the realities and vicissitudes of hardware that comes with sensors. Our LiDARs are always breaking down, and our angle of attack sensors getting dinged by passing birds, causing even the best laid algorithms to go awry. For further reading on how to cross this gap, I point you towards one of my mentors, Jaime Pizak, his excellent thesis on this topic. But I want to take a different approach to how we bridge this gap, the one that we most commonly see in industrial applications, which is that we will partner our automatically safe systems with a human supervisor who also understands safety and who brings their ability to think beyond the model that our systems have. As a concrete example, as the federal government is rolling out the next generation of collision avoidance, we still require not one, but two human supervisors to be watching the system at all times and to sign off on all of the advisories that this autopilot generates. This system actually uses a dynamic programming type approach, unlike the one we also use for reachability. And this partnership works great. It is the gold standard. And that's why in all of our classic manufacturing lines with machines, you will always see a human line supervisor patrolling up and down, making sure that the robotic arms do not grind to a halt or crush anything in the factory. In our power plants, we will have some monitors keeping track of the key critical states and ensuring that things do not go haywire. Even in our forward-looking applications, we will partner our self-driving algorithms that are hoping to hit the streets soon with these backup drivers to catch when they fail. And so this partnership is amazing. It complements the endurance and precision of machines' automatic safety detection with the adaptive, responsive, and flexible understandings of safety that humans are able to provide. Unfortunately, actually bringing these two elements together and fully leveraging human supervision is not as easily done as said. Because in practice, we need humans to be looped in on ongoing safety for them to be able to help at all. And to provide an example for why this is important, I bring up the unfortunate precedent of autopilot failures in recent years, where Boeing was rolling out the latest version of its venerable Boeing 737 model, the Boeing 737 MAX, so called because the larger jet engines were pushed slightly forward on the plane. This would shift the balance of the plane, requiring pilots to sort of relearn the handling. And so in order to minimize the amount of retraining that pilots had to go through, Boeing thought it would be wise to equip the machine with a bit of an automated algorithm that would augment the maneuvering characteristics to make it feel more like the old plane. Fortunately, this MCAS system had a fatal flaw, which is that it wasn't using redundant angle of attack sensors. And when the left angle of attack sensor got dinged and started reporting erroneous angle of attack readings, the MCAS started pitching the plane into stall adjacent and ultimately stalling angles. As we look at the records of the pilots trying to wrangle the system, we see that they do successfully push back on the system several times, but unfortunately the system is designed to un-override itself after a correction after just 5 seconds. So the pilots had to repeatedly push back. Because of a certain black box design paradigm, it was hard for the pilots to tell when the system was turned on and when it when it was turned off and when it turned itself back on. For more details, I again point you to. And so we see here that it's not enough for our systems just to be safe. They need to be transparently safe in order to maximally leverage human safety supervisors. This valuable resource for crossing the model gap. In order to make our systems transparent, we as model-based control theorists can generate transparent control as long as we have models of how supervisors judge safety. And that is what I will do in this talk. And I'll provide some concrete examples of how this can be done, how we can mathematically quantify human judgment and perception, and then generate better behavior for machines that make them more transparent. So in this collaboration between human and machine, we'll have one arc where machines learn more about humans using developments in statistics and machine learning. We're able to sift through the rich volumes of data that humans give us to learn more about them. And then machines can return the favor by helping humans learn about their safety or unsafety, such as it is. I've had the pleasure of getting to research and publish papers on both of these arrows. But the research I would like to share with you today actually occupies a space between where it actually works with both the green arrow and the pink arrow by first learning a model of human perception. We're able to use that model to generate behavior that helps them perceive and learn correctly, thereby completing a full loop. So today's talk is going to be structured into 2 parts corresponding to these 2 projects. In the first, we're going to emphasize the green arrow. We're going to emphasize how we can use machine learning to model human supervisory concerns. We'll then do a very basic way of adapting the robot controls in order to conform to the supervisor's concerns, like we might design a glove to fit a hand. In the second part of the talk, we will focus more on the pink arrow, instead preferring a very simple model of how humans perceive and judge, but then emphasize how we can proactively optimize controls to communicate safety. So let's dive right in. To set the scene, it's pertinent to know that there have been some great strides in not just machine learning, but particularly learning from human demonstrations. When a human acts and shows how to move through a scene, we can learn from their expertise. Here I have a video from Peter Beal's dissertation research. Let's play that video again. Where they had an expert human pilot remote controlling the plane, and then ultimately they removed the human since the plane, or the helicopter, was able to learn how to reproduce the human's aerobatic maneuvers through inverse optimal control, or inverse reinforcement learning, whatever you want to call it. For us safety heads out there, we can do something similar to learn how experts move around dangers and how humans consider risks, including some of my own research, which you can read about in the earlier chapters of my thesis that are not being presented today. But all of these methods work from how experts themselves move through a scene in order to avoid safety. But in this partnership between safety supervisor and robot, we're less interested in how they themselves would move through and more about how they would perceive and judge another agent being safe. And so the data we're interested in is actually these safety takeovers that we have on cars or sort of emergency stop buttons that you'll see on industrial robots. And what do those data signals say about how humans forecast dangers? And so to understand what we can glean from this very voluminous and wealth of data, it's worthwhile to think about the structure of these safety takeovers, which is that the robot will be doing its own thing autonomously, winding its way around the world until it reaches a certain state that the supervisor considers unacceptable. And it might not be even on the keep-out set. Why might that be? Well, the human has to intervene and then take action to save the robot. And so it's imperative that they not just save it when it's in danger, but before it's in danger. Particularly, there needs to exist a safe recourse. Mathematically, there needs to exist a control sequence U such that the future trajectory she is able to keep out of K for all time. This might be tickling your brain cells, from something we covered just paltry 10 minutes ago, where this is exactly the definition of a reachable set. And indeed, you can see here that we are opting to take the hardest right turn here in order to clear out from the danger zone. And so we see that these safety supervisor interventions don't just mark the border of the danger set, although they could, but they more presciently mark the border of the backwards reachable set, the states that are upstream of danger. What this means is that by analyzing this particular source of data, we're not just learning, gaining information on the constraint set K, but we're also learning how that particular supervisor forecasts danger, their particular dynamics F sub S that they use for generating these trajectories. Indeed, if the supervisor has a slightly different dynamic model from another, then they might generate wildly different interventions. Here, this user believes that the car can turn twice as fast as the one I showed earlier. And the reachable set is much more compact because this car is more capable of turning on a dime. In contrast, if the human believed that the car was more sluggish, then the reachable set would be much larger because more states would be doomed to peril. So we can see that if the supervisor has a different, and this all builds on a certain tried and true classic assumption within cognitive science called the noisy Newton hypothesis, which is that supervisors, or particularly any human in general, I shouldn't use particularly there, that generally any human, or when they're observing a physical scene, will forecast the outcome using some sort of crude approximation to a physics scenario. That's hence noisy Newton hypothesis. And this noisy physics engine might differ from the true dynamics. X dot equals, might differ from the true dynamics, X dot equals F of X U. So note that the supervisors dynamics are F sub S, and therefore they will generate a reachable set, R sub S, and a safe set, omega sub S. And these might not align with what the robot would calculate for their reach set. And this will be a source of friction between the robot and the supervisor. The robot is tootling along, it sees the obstacle, it knows it's there, it's going to avoid it, but it hits this set state here, which it considers safe, the human considers borderline. And they say, whoa, 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 bud, I'm gonna have to stop right there. You need to get out. So they would intervene, eventually turning control back over to the robot, continues working with the supervisor, it rolls forward, perhaps from a different angle, we'll just remap it on the same angle here. And they mark it again. And after just a handful of these kind of interactions with the human supervisor, we can already start to trace the contours of their unique reachable set. So this is the inspiration behind our work here, which is that we can learn supervisors' unique safe sets. That the intervention data is structured to be following these kind of teardrop shapes if they're watching Dubin's cars, and by sort of the equivalent reachable set family for different dynamics. So learning or analyzing intervention data this way, as coming from safe sets, we hypothesize will be not just an intellectual curiosity, but will be actionably useful in that following that safe set that conforms to human concerns will decrease unneeded supervisory interventions. And what I mean by that are times when the human thinks there's trouble, even if the vehicle knew that everything was fine and it was going to avoid the obstacles. This will drain sort of cognitive resources, driving up mental load for no good outcome. So as a, before I can get into the details of the algorithm, I need to define a couple more mathematical objects on top of the ones we've already defined, like the dynamics and the general trajectories and the definition of safety. That's this keep out set K, which is that I would like to define the sign distance function to the keep out set. L of x sort of ranges out from the walls of the keep out set here, getting larger and larger as you get more and more distance. And then is 0 on the border of the keep out set and negative inside. So with this continuously defined function that indicates set inclusion inside the keep out set based off of the sign, we can now extrapolate out safety in a continuous way, which is that we look over the whole time horizon of the future trajectory, xi. We find the closest it ever gets, the distance that is the smallest over the whole time. And we find the best case where we look at all possible controls, we look at the hardest left and the hardest right, and find out which ones get us furthest away from keep out set. So this v of x becomes a natural indicator function for safety. If v of x is negative, that means that no matter what you do, even if you're giving your best effort, you will end up inside K. And conversely, if v of x is non-negative, then you can be safe if you play your cards right. This is all good news. With this v of x, we can start to ascribe a continuous differentiable meaning to intervention data, which is that they should all lie on the 0 level set of v, particularly v sub s. So all of these points should be on v sub s is 0. This would be the idealized supervisor model. In order to be robust and get some sort of statistical guarantees, we should add some noise to this data, since all data will be a little bit noisy. And so let's first assume that the human might add some buffer. In full generality, they might not just want to skim by the obstacle, but they might want to give it, a foot or two of wide berth. So that will be their particular sort of padding they add mu. But then on top of that, we'll also add a Gaussian distribution. So it's centered around mu, and then it has some noise around it, some spread with variance sigma squared. And so the human will intervene on mu, which is Gaussian distributed. So with this Gaussian assumption, we can now see that human interventions, once mapped through this v of x function, will just be a problem of estimating a mean and a variance. It can be that with the sample mean and the standard deviation. But the v of x depends on the human's noisy Newton simulator that they have. And they could have a wide variety of possible mental dynamics corresponding to different dynamics of the vehicle. They could either turn very fast or very, very slow to the point of only being able to go in straight lines. And those generate this whole family of possible 0 level sets. And so all we need to do is basically fit the level set that best fits the data. We can do that by computing the best mu and the best sigma for each value function in this library. Ooh, that was long. So this model is all well good, but we're not cognitive scientists. We're not trying to prove what's going on in people's heads. We want to find something that usefully improves human-robot collaboration. To do so, we will run a test of pairing a human with a team of robots to really tax their cognitive load and their ability to supervise robots successfully. We play a simulated game with them where the cars are delivering deliveries from the left and the right of the screen. Every time they make a delivery, they get 20 points. But if they hit one of these obstacles, they lose 20 points. So it behooves the human to click on the obstacles to remove them. It's a bit costly, so they don't want to do it unless they really need to. And when do they need to? Well, we have hard-coded the vehicles to have their perception system fail 1/5 of the time. So most of the time, they'll successfully detect the obstacle, and once they detect the obstacle, they're guaranteed to avoid it because we're using those good, robust safety guarantees. But the human needs to catch this 20% of the time scenario. So I'd like to challenge you, like I did this subject number 9, to work with this top team and then later work with this second team. And when the cars are coming up on one of these, they're coming up on an obstacle, to try to predict whether it's going to swerve or not. This guy's coming up here, it's rolling through. Is it going to avoid this car? Oh, the subject decided no. Yeah. You can avoid, yeah, it does, but it's always the last second. Contrast that with the robots that are working off of the learn states, the states that learn from subject number 9. Here they are gently and gracefully turning well ahead of time and turning with a little bit of birth. And the subject hardly even needs to worry. You can see this reflected in their score. It's much improved. And anecdotally, they also had this to say about the team. While they were working with them, they loudly exclaimed, "I hate this team," even going so far as to call them "it's dumb." In contrast, the worst thing that they said while working with the team trained on their data is just a little bit of frustration that they were getting bored. Don't do all the work for me. Indeed, these robots were swerving exactly how the human would have swerved themselves, thereby preempting much of their work. And this bears out not only anecdotally, but also across the population of just 12 subjects, modestly sized user study, but the results were powerful enough to come through the noise, and we had statistically significant results of halving the number of false positives when using the state that is tuned to conform with the individual supervisor's concerns. Note here that we also had a second baseline, which is basically just to avoid all the obstacles with very wide curve. It was a clone of the minimum intervention. It didn't learn anything from the human. It just added an extra 1 unit of distance on either side. And then by being larger, by just swerving earlier, that was enough to preempt many of the user's interventions. This is the training set, or this is the amalgam of all the training sets from all 12 users. And so although it seems like you can just blindly turn earlier to reduce false positives, it's worth noting that, at least for, each subject had their own uniquely their own safe set, but at least for the case of subject 9, their swerving was much less circuitous, even though it still succeeded in having the number of false positives. So there's a certain trade-off between efficiency and transparency that is being struck here in an informed way. It can't be made with sort of blind swerving, blind kicking the long route. So in this section, we were able to learn human concerns, particularly as how they forecast danger. And we used reachable sets as mathematical structure, as an inductive bias, to induce efficient learning and deliver a very concrete, actionable advice on just how to replicate human alarms and human concern. And each of these points also opens up potentials for future research that I'm quite excited about. The first is that the data efficiency means that we could learn a safe set for each individual human. But it's worth asking, is it necessary to learn a safe set for each human, or is there a one-size-fits-all of supervisor concerns? My conjecture is that people with more anxiety that want the vehicles to turn earlier, or people with attention deficits might, you might see effects where when the number of robots drives up, the ability to intervene drops. And so it's worth asking how neurodiversity plays into human-robot collaboration and how we can help our systems work for all people or for a variety of neurotypes. This second point is more of a philosophical exhortation, which is that this research, by using tools from formal verification, is not the first of this kind, but it's another example of how we can model human intelligence with something other than the econometrics maximum profit model, which is so much in vogue for a lot of artificial intelligence type stuff. And there's nothing wrong with that approach, but it's worth noting that there are so many other tools in the control theory toolbox that are able to guarantee different intelligent outcomes and could be used to approximate intelligence, just like we did here today. So I would urge the researchers in my audience to consider other the whole span of intelligent controls as models for human behavior. Here, let me unpin the point I made earlier about just being able to swerve earlier, providing more information. Wouldn't the best of all possible worlds be not even to swerve here, but instead of just swerving at the last second, albeit from how the human would swerve themselves, instead, as soon as the car comes within sensing distance of the obstacle, swerve early so that you give the humans the heads up that you're going to avoid and just preempt all of these data points. There's no need to even get close to making them worry. In this sense, this motion has an information load, where it is communicating something to human early on. It's anticipating the fact that it's going to avoid danger. So how can we formally generate motion that anticipates danger and is aware of this communicative aspect? That is the purpose of our second part of the talk, where we're going to use a fairly simple model of human observation and human perception, and instead really hammer home this proactive communicative aspect. So our goal here is to be able to look at trajectories like these, returning again to our student's car example, and have them not just technically avoid colliding into an obstacle while still reaching its goal, but be able to move in such a way that it efficiently reaches its goal, but it, by this sort of 2-second mark, makes it quite clear that's going to avoid the obstacle, whereas the difference between the unsafe path and the just safe path is quite hard to discern if you weren't able to see the rest of that future trajectory. So this research, of course, builds on prior art, where Dielniak, working under Tamaz at Georgia Tech, and now UT Austin, recognized that human-aware motion shouldn't just avoid humans as obstacles, but that motion is communicative in and of itself. And they were inspired by the principles of hand animation used by professional animators of their ideas of exaggeration, anticipation, secondary motion. Dielniak translated these into mathematical objectives that can be algorithmically used to generate expressive motion. Dragon then took these and re-derived these ideals from a sort of first principle, a theory of mind drawn from computer science, where they assume that the people are using a sort of naive utility calculus in the attentional stance, where the inferring human is watching the trajectories as a sort of evidence towards nudging them towards one hypothesis or another, where the hypotheses are the possible intended tasks and purposes that the robotic agent might be working afterwards. Giordano and Cervasa assumed people were like a little econometricists. You can sort of reference here Griffith's paper about babies as econometrists, where more profitable choices toward the intended goal, H, are exponentially more likely. And then less optimal things are still possible, but less likely. And this distribution models some uncertainty in the true rewards, where there might be some hidden preferences that the econometricist is unaware of. And so to get a bit concrete, let's tie it back to our grounding, motivating example of the car moving through space here. This is something I might want to change. Yeah, I need to change the Z's and I need to change this picture. Okay, cool. Where the human is trying to infer whether the car is either just doing minimum effort to reach its goal or doing minimum effort and keeping some distance from the danger zone. And so you have this sort of unsafe hypothesis and a safe hypothesis. We can number these hypothesis 0, hypothesis 1, and I'm not just zero indexing because I am a good-hearted computer scientist, but also because I want to draw a connection and spark in your mind the connection that this could be the null hypothesis and the alternative hypothesis, summarized by these objective functionals J sub null hypothesis and J sub alt hypothesis. With this analogy to hypothesis testing established, you can then say that if the human is doing hypothesis testing, well, by golly, if they're rational, they should be doing the uniformly most powerful test. They should be doing the Neyman-Pearson rule of communication theory to test binary bits. This is all just fancy speak to say that you should take the ratio of the likelihoods of observing particular control choices given the null hypothesis, unsafety, and the alternative hypothesis, safety, and divide them by each other. And note already that this hypothesis testing framework for the two agents is already radically simpler than, or not radically, it's a little simpler. The radical comes later. It's already simpler than the Bayes belief objective used in prior art, which had this addition in the denominator. That might not seem like too much, but it will become a real thorn in our side for once we consider this distribution of U's given intents. So let's dive into that. This econometrics derived model, the random utility model, distributes the probability of chosen control trajectories based off of how costly they are. The more costly they are, the expansion more unlikely. And then you have to normalize this. And if you just abstract their way into the Z, this seems not too bad. Once you break that normalizing constant apart, you realize that you have to, these would be separate, sending to a dummy. All right, 3 is the point where I'm going to start writing this down. Okay. Y theta instead of y theta. Picture hypotheses. Then here you need dummy variable integration. C sub H. Cool. You have to integrate this exponential over all possible controls, which for continuous time is literally an infinite dimensional space. That some will be a bit difficult to pull off. Fortunately, Giordano and Cervasa were able to identify an approximation. If J is quadratic or roughly quadratic, this integral can be approximated as just the exponent, the integrand evaluated at the minimum, the minimizing U. So that's a big improvement, but still requires us already fully solving the optimal control problem before we can even just define probabilities. This is a a situation to say the least. For, again, quadratic costs and linear dynamics, this isn't so bad. You can solve that with LQR. But in general, this can get quite woolly, especially for non-polynomial systems, or the ones we are considering. Fortunately, obtaining this normalizing constant becomes a non-issue for the likelihood ratio objective. For the likelihood ratio, because you're taking just a simple ratio, these multipliers don't have to worry about any sums. They just factor out evenly. And because we're guaranteed that they're non-negative, they are irrelevant to finding the critical points of lambda. In fact, while we're at it, this e is a non-decreasing function. Therefore, we can just compose it with its inverse, the log. Just take the log likelihood ratio, and you'll have equivalent critical points. And lo and behold, we derive this objective whose critical points are maximally communicative. That is just a simple difference between performing well on the true objective and then you want to perform poorly on the false objective that you want to distance yourself from. This is very intuitive. This is probably what you would assume in the first place. But this simplified structure was obfuscated in by the Bayes structure that we had assumed in prior art. By revealing this simple linear combination, we're able to get objectives that are generally in the same computational complexity class as the pure sort of uncommunicative objective, J sub H1. To see this in action, let's recreate the application of Dragana-Srinivasa, where you're just trying to show the only difference between the two hypotheses is what end state they're trying to reach. So they only differ based off of this ending penalty, X. Goal 1 and goal null. Dragana-Srinivasa was working on the high-level path planning problem, so they were able to choose their X at every following time point. So in effect, X1 dot equals U1, X2 dot equals U2. They just got to choose their velocity at every time. It's fully linear, fully controllable. With the Bayes belief objective, they had to run this through covariant Hamiltonian optimization for motion planning, their CHOMP algorithm, which is a nonlinear planner. Go to self, check whether it's nonlinear. Use CHOMP. And it's also past 9, so I should go home, huh? Oh, if I'm going to get that second bit there. This is true. This is true. But in contrast, when we are just able to subtract these two objectives, we're able to recover, take these two quadratic costs and get yet another quadratic cost. And these linear dynamics stay linear, and so we can fully just solve this via LQR. No nonlinear solvers are required. In fact, this is so simple that I can afford to compute it multiple times over during the time horizon and still realize real-time execution. Oh yeah, real-time computation, not execution, because we didn't run some of the system. That's not something I'm going to try. Real-time computation. Yes, what was I going to say? Real-time computation. Oh, yes. This is a perk because we were able to recreate one of the ideals of Bielniak of having anticipative motion, which is extra communicative early on, and then worries less about communication towards the end. So we're able to change the weights between being communicative, distancing ourselves from the null hypothesis, and then just focusing on the fundamental true hypothesis later on. But we were able to do more than just recreate prior art. We can go beyond it. Now with our more tractable system, we can communicate more types of intent than just end states, including, most critically for communicating safety, rules that run throughout the whole bulk of the time horizon. Here, we're still in a sort of motion planning framework, So we're going to avoid obstacles based off of a potential fields type, repulsion from danger. And then this would be hierarchically compounded with a low-level planner like the reachability intervention to guarantee safety. And so with this communicative motion, we're able to show after just 2 time ticks, we're able to see very clearly that it's going to sort of around the obstacle as opposed to the path that is just safe. This holds up well, coming to our running example from the top. Now we're able to generate motion that is able to really differentiate between the just safe path and the unsafe path. Instead of just skimming by the obstacle after 10 time ticks here, it makes it exceedingly obvious, even after just 5 time ticks, it becomes very obvious that we are avoiding the obstacle rather than crashing. The takeaway here is that caring for humans' needs for information doesn't have to be complex. It can be in the same computational complexity class altogether. And so simply considering human needs can be practically free. And how can it be free? It's worth noting that by taking this simpler model, this simpler approximation of human behavior, we lose out on some details. We can no longer model prior beliefs, competences on the robot. The ADA that would reflect humans' leanings towards one hypothesis or the other is completely ignored when we're just minimizing. But by sacrificing this detail, we get a objective that is much simpler and can be run on a variety of formulations. This continues all the way up, where work that followed on from Japan's from our very own Physac, as well as Collaborators, Gates, Hammer, Blue, Hatfield, Al. We're able to include some multi-agent game theory in this communication and realize that the student knows that the teacher knows that the student is trying to interpret, and then the teacher knows that the student knows, the teacher knows that the student knows, the teacher knows, and you get sort of this game going on forever. They were able to find a sort of convergent point of this shelling game and reduce it to just a partially observable Markov decision process. Unfortunately, partially observable POM-DPs are famously cursed as far as the curse of dimensionality goes, where the belief space planning blows up fast. And so solving a POM-DP is basically mostly doable in sort of high-level games like this. So what we lose in fine-grained detail of capturing the unique aspects of a particular human, we gain in simplicity. And particularly, we're not just losing detail, but we are distilling down the essence of what we want to capture. This cartoon captures the sort of essence of a human with short hair, as opposed to this very specific Scott McCloud character. It's worthwhile to strike the balance between after we discover a wealth of details that we might want to model, to then go back and distill it down to the vital essence that is necessary for completing the task. So in these 2 talks, or in this talk, in this part, we were able to provide a simple model of human inference, particularly as hypothesis testing. And then from there, we're able to practically optimize controls to evidence safety, in the sense that the human is like a scientist comparing hypotheses, and they're evaluating evidence between the 2. And this is particularly germane for CITRIS supervisors who have to critically examine systems to determine evidence. They cannot naively just trust what the robots are saying, but they need to know that the machines are putting the money where the mouth is and evidencing safety. So take a step back and look at the bigger picture. We now have 2 different illustrations of how machines can first learn about humans through a simple cognitive model. and then use that understanding to help humans learn about machines. I'd like to conjecture today that once humans understand more about machine safety and unsafety, they can then improve the data that they're providing to the machines. And then we can have humans help machines learn about humans. And this forms a virtuous cycle where more understanding of humans provides more understanding of machines, provides more understanding of humans ad infinitum. In control theory, we like to call this a positive feedback loop, which will blow up to infinity. For states that we want to keep stable, that's bad. But for mutual learning, which is a strict positive, I don't mind if that increases to infinity. So let's create a feedback loop of human learning and mutual understanding. This mutual understanding was not only going to be vital to the people behind the wheels who have to save otherwise opaque systems from certain death, but it will also be handy to all humans who have to collaborate side by side with these machines. Continuing with the road example, we see that in our current rollout of self-driving cars as they hit the streets, that most accidents are actually caused by what should be safe behaviors, by not charging through stoplights, but instead hitting the brakes. These safe stops are too opaque to be safe. It causes other road users to rear end or sideswipe our machines. So we see that transparent safety is vital not only to safety supervisors, as we've mainly been concerned with, but also with all the entire populace and society of humans who have to collaborate with our machines. So as our machines are becoming increasingly not just reportees to humans, but are becoming side-by-side collaborators in our streets, in our factories, and even in our hospitals. I hope that this research has convinced you that we can build machines that proactively support human decision-making and a diverse set of human decision-making through detailed models. And that will create a safer society. Thank you for your attention. Let's make that feedback loop of mutual understanding. Thank you. Particularly thank you to all of the wonderful community here at Berkeley that made this happen. To all the people who here on the third floor work on safety or human and robots together, or just building wild biomimetic systems, getting to eat with you and learn from you, and even just heckle AlphaGo as it makes its debut, or learn that you can assemble a camera tripod out of sticks. You all have taught me how to wonder and ask questions boldly and with a vengeance. In particular, not just the third floor of office mates, but also the broader CITRIS People and Robots initiative. I had the good fortune of getting to organize a graduate roundtable with awesome people like Katie Driggs Campbell and Michael Lasky. And with that community, I got to meet people who I would never have overlapped with otherwise, like Megan Clark. And old what's his face? It's Alan Baum. Maybe for the crowd. If Alan's not here, that joke will fall flat. I like it. I think it's funny. Anyway, also people like Megan Clark and Alan Baum. Big thanks to them for broadening my horizons. Also have to especially thank, as we're exiting this protracted period of quarantine and shelter in place, on the people who defied solitariness with me and helped keep me accountable to be really hit my stride as a publishing researcher. Big thanks to Victoria and Jamie and Kristen and Laura, the people in the accountability bubble, my accountability buddies. And of course, I must thank my buddies in general. Things in research don't always go well. It's important to have a sort of diversified portfolio of happiness. So get yourself some awesome people to play Dungeons and Dragons with, or to discuss theology with. It's a good old time. Also, having a good place to crash is paramount. I have benefited so much from the 3 houses that I've had the good fortune to live in. They were not just houses, but homes, and places of sort of ambient, welcoming fellowship and fun. I hey, if you're here in person, you have a physical body, that means you live in the University of California. And hey, the UC Martial Arts program is here for you, not just to learn how to hurt people, but how to not hurt people and not hurt yourself. To be gentle with yourself, be gentle with others. The Self-Defense Young Widow Club is the best community for this that I've ever met. Highly recommend you check them out. The wonderful instructors there are second to none. All this research that I got to share with you today would not be possible without my wonderful collaborators who encouraged me to keep on it even when things were spiriting. I say dispiriting a lot. Grad school's not all flowers and stuff. I'm a very flowery person, but it's important to communicate. Yeah. Dexter Scobie, Joseph Menke, Alan Young helped with that part one that I discussed, and invited me in to be a collaborator and contribute to the science that's happening here in the FHL Live Center. I've also more recently gotten to see the rising stars of great scientists like Kayleen Stockton and Victoria Tuck. And let me tell you, it's one of the, it fills me with pride to say that I knew them when. Keep an eye on these two, they're gonna crush it. Yeah, big thanks to them for asking me questions and making me feel like I actually do something and letting me be a contributor. Along those same lines, I have to thank all my students who I got to work with. I didn't get to present their research today, but just getting to see the wild array of fun times they got up to and all the projects that they built. Too many people to name all at once. Just getting to work with you, always asking the dumbest questions and taking the mightiest swings. There's no such thing as a stupid question. And the dumb questions are generally the most cutting to the foundation of misunderstanding. So always have boldness to ask. You are an inspiration to me. Of course, I would be remiss not to thank my committee who made this program into broader discovery possible. I have to especially thank you for creating this environment that I just praised for 5 slides. Bringing people together who are curious, inquisitive, helpful, and kind is remarkable. Claire put me in contact with people like Margaret and Kene and Shimona, who gave me my first projects. Under Shankar's easier, I got to meet wonderful people like Dexter and Joe, as well as other people in the Trust Center like Katie and Aaron. So this environment that you've created is truly opens the doors to wonder and possibility. And to you specifically, I have to thank you for your wisdom and encouragement throughout my years here. It has been formative, to say the least. But finally, I have to give my due to filial piety from taking me from this scrub who's doing computing inside the box, to thinking outside the box to serve human cognition, all the way to launching this travels on this faraway coast of the Pacific Ocean. The first credit goes to my mom, who taught me that the Latin words for school and fun are the same, and that learning indeed can be fun. All the way to my undergraduate thesis advisor, who always came with a smile to electrical engineering. And then in between, all of the wonderful old hands in Chattanooga who helped me, let me fart around in their garage and build things and realize that you can turn just something that's an idea you dreamt up into physical reality. Cheryl and Bill Ayers, Ed Chapin, and most importantly, my grandfather who passed away during my preliminary exams. My thesis work is dedicated in hopes that other people will get to see the world of engineering like the one that he opened up to me. I also should thank my broader set of all of my siblings. That's interesting. All 9 of them and 3 siblings-in-law, as well as these scrubs weren't able to make picture day. My fellow West Coast brother and my dad. Y'all did good. I must say to all of you, my collaborators, office mates, mentors, and kith and kin, from the bottom of my guts, I thank you. owe everything to you.